Well, no, is it H?
No, it's not H.
Oh, that would be great. Triple H. I would have called you Triple H from now on.
Yeah, that would have been funny, but no, it's R. Of all letters.
HR. Nah, that's not as fun. I have a middle name H. I was almost HHH.
That would be sick.
Oh, you brought the microphone. Oh, yeah. Pull this for a second. Would you like that little piece of paper I gave you last time? Oh, that doesn't matter.
Origami.
Huh? There's a big tangle mess.
It's like a little makeshift tripod. Does that qualify as an origami?
Maybe. Maybe. It's functional. I don't know if origami is functional. Is it mostly aesthetic or is it also functional? Could you hold this part? Just pull it. Put it on the table. Put it on the floor. Tripping hazard.
I just summarize the end of last class, then we can keep continuing. So here, just remind you where we are last time. Okay, here we already prove that is I think that is almost end of the last class. Now we keep continue. The topic is we consider the conservative force associated with conservative force, the potential energy, right? So we consider for ice particle, light force and ice particle are two parts, external and internal. For the external, we can separate into either conservative force or non-conservative force. Then for the internal, the force also conserved force or non-conserved force. So now let's look first this term. Associated with this external conserved force, we know there must exist the potential energy field, right? So we introduce V external, the ice potential correspond to the the force for this ice particle, the conserved force, the gradient, right, respect to the ice particle. Then we look this the work done by this conserved force, external conserved force. What we found it is nothing but the decrease of this potential energy, external potential energy. If we sum over all the particles, then the sum over all the change of the potential energy. So we introduce total external potential, which is associated with external field, right? That is sum over for each particle. There is an external potential energy for each particle, sum over all. Second one, let's look this conservative force, that the internal conservative force, right? Gi conservative, since it's a conservative force, we know that's been associated with exists the potential energy. Now we introduce Vig. That is correspond to this force. The gradient of Vig give us the negative gradient is this force, right? Here, this respect to, because this is a force of J particle act on the ice particle, right? So I use I here, that in gradient the partial Ri. Then we already, last time we already proved that is equivalent to the partial derivative of Rig. Remember? So that is, we down to here. Then we apply the Wick, right? The Wick law of action, reaction. Then we have, since okay, because we have this, so we have this gradient of Ig, Vig equal to negative gradient of Gi, Vgi. We first have this, right? Then this is apply the Wick, but then we apply, next we're going to apply the strong law of action, reaction, since we also say that the internal, the force always proportional to the Rig, right? Either a parallel, right? Sorry, not proper parallel, either same direction or opposite direction. That is required by this. If by this, so we have that. You can see here, this force, so this force is proportional to the negative gradient. Let me see. Okay, whatever this, I use this Ig, right? Ig. Then, if the force is parallel to this, so this one should be, the direction should be along Rig, right? And then this gradient is only the numbers or absolute value of, not absolute, because it's maybe negative, maybe positive. So here, now this is only dependent on the absolute value of distance. So that means this gradient, the potential Rig is only dependent on distance between I and G. Does not depend on the direction. And then the gradient is parallel to this Rig. So when we have this, then you can see here we have, in this case, then combine these both. So we have here, you will see here, this gradient is only depend on this direction of Rig, which then you have the change index. So here, so we have, okay, Ig Vij by definition is partial Vij partial Xij I hat partial Vij partial Yij J hat and partial Vij partial Zij K hat. And then I'm going to take, because Xij is Xi minus Xj, then Gi is just a negative, right? So now I can do this, Xgi. You agree? Xij, Gi is just up, right? So now I have a negative sign. Same thing for the others. Partial Ygi. And what that means? It is negative delta Gi Vij or Vgi, whatever, because this one is only dependent on the magnitude. So I see here, okay. I can change, so now let me do this way. Okay, yeah, let's do this. So now we have this, right? And then from the weak law, this one equal to negative of delta Gi Vgi. And we know this is equal to negative of delta Ij and the Vij, delta Gi Vg. So that means they should be the same, right? This one should be equal to same. I mean, this index, even though I change the Vij and Vgi, they are same. So we have this conclusion. Ij, delta Ij Vij equal to negative delta Gi Vgi. Oh, that's enough. Yeah. So here we have this. Then now we are going to look this term. The force Gi, consider force, right? Do the work. Move the S particle with a displacement dri, and plus, since we are going to consider a pair, so Gi and Ij consider force, do the work on the G's particle, move the G's particle drj. So now let's look at this one. Then we have this. We have a negative delta Ij. Okay. Negative delta Ij Vij dri minus, and then this minus will become plus, right? Okay, let me first, not check. Minus delta Gi Vgi drj, right? Now I'm going to take this, keep this, the first one, keep, so V delta Vij, delta Ij Vij and the dri. Now this one is equal to this, right? So and then it is also, because this one should be equal to negative Gi Vgi, because they are equal, right? This one equal to this and also equal to, so they are equal. So I'm going to replace here, that is a negative. Okay. Now plus, because this one is this, right? So now we have this one is plus Ij Vij. Okay, here Ij, right? So is this one. So I can replace this and the drj. Then I take the next sign, negative sign outside. So I have a delta Ij, okay, Vij, and inside the dri minus drj, which is drij, right? Okay. So once we know that this the pair, the work done by this pair force on the two particles is equal to this, then we can consider very easily is let's sum all together. we have all the particle I from 1 to n, and each j particle, the neighbors which not equal to I, which move the particle, the whole system from 1 to 2. That is all these ji conserved force do the work on this one, right? This is sum total. Now we're going to make a pair. So when we have this summation, extend this summation as a pair, so we have a half of from this I from 1 to n, and the G is not equal to I, but each one, let me just write down the intermediate. So now this is the F G I conserved force, DRI, and this is IG conserved force, DRG. Is this one. And now you know that is equal to negative half of I from 1 to n, G not equal to I, and it's a delta Ij, Vij, Drij. We were given, I have all integral, right? So I need to have integral from 1 to 2, from 1 to 2. Then you can see here, this is delta Ij, Drj, so they cancel, right? So now it is negative I from 1 to n, G not equal to I, and the total from 1 to 2 d Vig. So that is the difference of this potential energy. Then okay, please continue. Then that is equal to the difference of this, or decrease of potential energy from 2 to 1 for all the particle. Sum of all the, so that is Vig2 and Vig1. That is the whole work due to this internal constant force. To the whole part, the whole system is all the particles, right? So with this and similar like this, therefore we introduce this total. Okay, so now we are going to introduce total potential. Since we have a potential due to the external potential energy and also internal, right? Yeah, please just pass this sheet, partition by, yeah, sign this. So we have external, that is sum of all the particles from 1 to n. Each particle has its external potential energy, and plus the, here I have a factor 2. I from 1 to n, and all the j is not equal to I. If j equal to I, then this factor 2 will disappear, right? And then Vig. So this we introduce total potential energy for the n particle system. Now when we go, before we go to next to see the total energy, since we have a potential energy, we have kinetic energy, we can have the total the energy, right? Before doing that, let's do some example how to determine this total potential energy. Let's do some examples, like how to determine this total kinetic energy. I give you the way, either you sum over all each individual particle's kinetic energy, or you make like a center of mass kinetic energy and plus relative kinetic energy. I give you some example how to, which one, how to determine those, right? So now let's see how to determine total potential examples. First one, let's consider again, we have a disk and rolling down from this incline. So suppose we have the location here, and we have a mass here. This velocity center of mass, and we have a center mass of distance. This height is h. So let's see how to determine the total potential energy for this case. Since this disk formed by the n particle, right? So usually you have this potential, external potential. Let me write down in general, and then we can analyze Vi external, right? Plus, let's internal, okay. I from 1 to n, J naught equal to I V I J. How to do that? Okay, the first one, since we consider each particle you have, they come from the external gravity, right? So that is gravitational potential energy. Gravitational potential energy that for each part, you consider the disk formed by the n particle. Each particle has the height, right? Then you have the.
So I think the rotation will be in this way.
Yeah. Okay. This equation. And then you just sum over all. So this case, you will, very easily, you will see that is nothing, this center of mass. I'm going to say this is the total mass. Multiply the h. The h is the center of mass if this is 0 as a reference. So that height, you will prove yourself it is equal to this. So that means this term is here. And this one, that is the particle between each I and J. And the distance always keep is a rigid body, right? So that is constant. We do not know, we don't need that, just constant here. And this constant, when you consider dynamics, it will, doesn't matter, right? So that is a constant. So that is the way for this, you analyze the total potential energy of the system. Now let's do the second one. I think we did the same thing for the kinetic energy. Now for the system, for the potential energy, we have poly here, hang on the shading here, and then there's a loop. At the end of loop, we have another 2 box. Overall, you just consider as a point. So here, 3. Okay. So in this case, now we have 3 systems, right? Big system, but then let's consider total. Again, from 1 to, let them just say n, right? So, okay, let me do this way. Let's consider these 3 systems, right? So now V1 external, which come from gravitational potential energy plus the second one and third one, right? So that is the summation of this. Then plus this internal. Internal, there's 1 between 1 and 2, between 1 and 3, between 2 and 3, right? So now let me just say, let me just give you 1, 2, 1, 3, 2, 3. We do not know how much, but this is the internal due to the gravitational, because it's a mass, right? So this is from the Earth, the external. Okay, and then in principle, since as we analyze here, these are for this, the poly we have also a lot of the particle form this, you can consider that is a half of I from 1 to n. I just use this formula here. Now I'm going to use index 3, Ig, right? This formula. And again, if we select that, just make this, because this is fixed, right? So it will not change. Only this M1, M2 up and down. So if we select this one as a horizontal, as a 0 potential reference, therefore we have a V1 external, V2 external. That depends on how much you say that is x1, x2, right? Details. And then this one is 0, right? Since I select the center mass as a 0, so the external potential on this poly is 0, since we select as 0. Otherwise, it is a constant. Then, okay, I'm also going to say that 0, that's ignorable. Because what? This is a gravitational potential between those mass, and this mass is very small, M1 multiplied M2, compared with the Earth. Right, so this is ignorable because very small. That is potential energy between the mass, right? Remember? It's the potential G for gravity is equivalent to the constant M, Y, Mg, R, and G. Right? So if this product compared to the Earth's mass is much, much small. This is from the Earth's mass, right? So that we can draw, and then plus constant. Since this half segment like this is some constant here. So the majority, the dynamics is determined by these first two, right? So that is this case. If you select this, whatever if you select the potential, because this poly is will not change the up and down, so that is always a constant. If you select that constant as 0, then you just set 0. The third one, if we have this two like a molecule or two particle connect by the spring. Suppose the spring the at equilibrium is L0, and then this distance x1, this distance x2. Now in this case, the total potential energy of this system will be V1 external. We have external gravitational potential energy on the particle 1, and second one external, and then plus the internal is V1, 2, right? Okay. The internal is actually you can say that is internal or external. It's fine. If we consider this is only this interaction is through the spring, right? So whatever, so just give you this one. It's if I write down this from 1 to 2, right? Not equal to I with Ig. All right. So now this one, since this motion is only the horizontal. Only the compressed strings, and with this center mass or this MM2, not the vertical. So we select 0. This is 0. This is also 0, right? So only that term. That term has a come from this spring. The first one is supposed to be have because spin the constant is k half of xy squared plus x2 squared. Right, so this gives you the way how we determine the total potential energy for the n-particle system. Now, we come to the total energy and the work done by the total force. So that is work energy theorem for the many-particle system. So now, let's consider the total work done is by this n particle from 1 to n, from 1 to n, and this I net. Then we separate this into this inner product. Separate into the conservative, non-conservative. So we have I from 1 to n, 1 to 2 I conservative. Now this concept includes both the external and the internal. I just write down this way. And plus integral. This is I non-conserved So the first one, we know that is nothing but this total energy difference, potential energy difference, right? So that's V minus V total division 2. V total is 1. That is from here, and then I'm going to say those non-constant force do the work. We call this non-constant work done by non-constant force. Then the left-hand side, we know that is total kinetic energy difference, right? 2 minus total So we have, if we move the potential total percentage to the left-hand side, we have this E total, the total energy at position 2 minus the total energy at position 1, which is equal to the work done by non-conserved force. Non-conserved force. This is work energy theorem. And here we introduce what is the total energy of the system is total kinetic energy plus total potential energy, and the total potential energy include is the total external potential energy plus this all this internal potential energy. Okay. So up to now, we have briefly reviewed the Newtonian mechanics. Let's try to summarize. Then we are going to go to the next step, which you will see how difficult and how to solve this difficulty, right? So brief summary. First, for the total linear momentum, the dynamic total linear momentum, we found that the total dynamic linear momentum is controlled by the total external, right? Or net, let's use net, since I use net always, right? That is only need a weak law. Weak law of action, reaction. Right? Then second, for the total angular momentum, the dynamics of total angular momentum we've also found that is controlled by the total net torque, external torque. That is followed after if we apply the strong law of action reaction. Here, one more information is this also equal to the center mass, linear momentum of center mass, right? This is equal to the summation of the angular momentum of center mass plus the relative angular momentum, total relative angular momentum that each particle rotates about the center of mass, right? So that is details. Now, that is for total. For each individual, since we are going to solve the dynamics or equation of motion for each particle, how each particle move, that is follow the d linear moment S particle. That is follow this the Newton's second law that gives us to be total net force on the S particle controlled by net force. And the net force include this external and internal, right? Okay, this is internal G not equal to I F G I. All right, so you look this, the formula looks is kind of simplified since not so complicated. Look at the formula, right? That is Newtonian mechanics. So what we found is those equations of motion is simplified mathematically. That means mathematically it's just a second order or first order partial derivative, right? If you consider this is consider the position is second order. But Okay. But you know that this is how many 3n equations, right? Each particle has a 3 x, y, z direction, so we have 3n. So these 3n equations are usually are not independent. That makes this to solve those it's not easy, right? Are not independent. This is make some of difficulty. The most complicated or difficulty number 3 is each one you need to analyze force. So each case, the specific you have for each particular specific case, you need to analyze the force in particular for n particle system. If you miss one of them, you make mistake. You cannot solve, right? So the difficulty or complexity is from this force analysis. That is very complicated, right? You have to carefully to characterize all the possible force. The reason why, let me show one example. You may, I hope you can agree that is how complicated. For example, okay. Now, if we have this free, so that is a free particle, right? Or free system, rather a free particle. That's a free motion. So you have x, y, z. No any restrict or no any limitation. That is free. But how about this? If we have the box here, which this is surface. That means restrict is restricted on the surface. The motion, right? The motion is restricted. Then let's try to analyze the force. You know this, at least we know this limited so that there's a normal force, but this normal force always change the direction, change the magnitude during the path, right, on the surface. Can you write down the formula of the force for this? It is not easy to straightforward to write down, right? So if not, we cannot go further, right? So that means, yes, this Newtonian mechanics looks mathematically simple, but when you deal with the details, it is not easy. In particular, when we have this type. So now we are going to focus on this. And our goal is try to develop the theory such that we can get over this, or overcome this, or to solve this kind of problem. To find this more general way to solve this dynamics of this, or motion of equation for the equation motion for the system. So now that way we introduce constraint concept. So now we are going to discuss constraints. What is constraints? All the limitations on the motion, right? If we have on the motion, if there are any limitation to limit or restrict its motion, those we call the constraint. And the force, constraint force, that is a force either say generated or associated. Okay. Constraint force is generates the constraint, right? Simply say. The force to generate the constraint that is the constant force. So that means when we analyze it, whatever, let's come to here, the total net force on each individual particle, there are some of force belong to that. So we want to treat those difficulties and find a way to how to overcome those. So we are going to classify the force. Now we are going to classify the force in terms of not external, internal, applied. Now the net applied plus constraint. Maybe there are several constraints, right? So that is over. Yeah. And this one is a troublemaker, right? Maker. That make this difficulty when we solve this equation motion. So now we want to solve this. That is original idea, try to develop the analytic mechanics. Okay, so now this one, the reason why we said troublemaker because it has a difficulty is that first cannot be expressed straightforward, right? So the force, let me say. Force cannot be expressed straightforward. No space. Okay. If not, then we cannot down to here to solve this mathematically, right? Second one, if you reduce, so the constraint, because the constraint exists, reduce the degree of freedom. If there's no constraint, this particle, the degree of freedom is the whole freedom, right? That is 3-dimension. But if you have constraint, they are limited, so the degree of freedom also is reduced. That is makes difficulty, right? Make difficulties or impossible difficulties. So equation. Okay. So now, before we discuss how to overcome these difficulties, we first classify, give you the what type of, they classify this type of constraint. When we have this classified, then we are going to discuss under which type of constraint we can go further, right? So now we are going to discuss here. This means we cannot directly or express this force straightforward, but at least we know the effect of the constraint. Like this, we know it's always limited on the surface. So if we know the effect of this x, y, or the coordinates of this particle follow which type of the equation, then we can categorize, right? So even though we cannot write down the force, but we can write down or analyze what is the associated with the constraint. So that means we have the equation of constraint. That is the effect of constraint on the motion, right? So now we know that how this constraint come from and what kind of effect on the motion. Then let's set up that effect mathematically. That we called equation of constraint. Examples. We have like this. So if the x, y, z, so all the n particle, each particle has its these coordinates, right? So we have n particles, and then the n particles, the coordinates follow some function. I'm going to say f. What kind of function it depends? Equal to 0. So that means like if in the n dimension or 3n dimension, if you have some constraint, the dimension reduce, like the n-1 surface, right? You can imagine. Like for example, the 3D, 3 dimension, the particle, if no limit, it move in the whole space x, y, z. But if limit on the sum of this surface, so this x, y, z follows some function, and that you imagine is a surface, right? Whatever surface, maybe spherical, maybe box, maybe. So that kind of surface. So that surface gives us the relation between these coordinates, that is the function, or also this has the time dependent, or not only the position but also the gradient, the velocity. Or it is not equal. It's a lot.
So constraints are like, well, basically like friction, air resistance, all those are constraints.
Yes, later I will show you example, you know what this. That means the constraint means they limited the particle move in the space, right? So the particle's position, coordinates, will limit it in a certain, or have some relation, because this constraint will set up this reduce the degree of freedom. And how to limit it, how to restrict, that gives us function. I'm going to show you how this, but this is mathematically in general, that's be a function, get this, right? So now, those are equations constraint, and there are different type of equations constraint. So let's first give a type. First type, we are going to consider this case. If only the function of the coordinate either without time or with time, these are we called holonomic. So type of equation. Sorry, just type of constraint. First one, okay. Holonomic constraint. So when we say holonomic constraints means that only the coordinates, or with time or without time. That means dependent on time or independent on time. If this case, if your equation of constraint is only the function of coordinates and time, then we call it is holonomic, and must be equal. Not this one is not, right? Either larger or so it's be equal. It's holonomic. That means okay, that is one case. Now, Akil, right? Akil asked the question, what is details? Let's show some example for this case, right? How to write the constraint. For example, first one, let's consider rigid body system. So rigid body system, let's consider we have a body here, and we have whatever we have A and P. Okay, A, particle. Yeah, just A position here, and another position is P. So the distance here are, maybe IG is better. Okay, Rij is constant, right? Whatever. Once the position here, whatever the system will move, but the relative position between the ith particle and jth particle always fixed, right? That is rigid. So this one, I can write this way. It is fixed, constant, right? So if I take the constant, it is take square is again, right? So that means R, this one is Ri minus Rj square, that is magnitude, is minus C, what is the distance between these two? Always 0, and Ij is equal to 1 until n. So this one is fixed 1, and for example, R1, R2, and R1, R3, another distance. So this is a whatever change, but this is constant. So each pair always follow this. That means this difference distance always is equal to constant. That is equation. That is this one. That means you have all the all the coordinates and follow this. That equal to 0. That makes sense? Okay. That is one example. Let's go to second example. Second one, like simple pendulum, which you are familiar, right? A simple pendulum. Okay, so that picture is like we have. Okay, so this is X, and this is a Y-axis. Then we have the particle here that is with L fixed, right? There's a mass here. And at any position we have x, y, right? And the A will move, right? Okay, now we just move this one over this direction. So this is a pendulum. Now, whatever the change, we know it always restrict the distance between M and to this origin here, always L. Yes.
The example, rigid body example.
Yes.
Is it bracket in the down, or is it a modular? Like
it is a bracket. Bracket with part.
You mean like the distance, right?
Yeah, this distance. Yes,
okay.
This is Rij magnitude. That means
Yeah,
the distance between.
It's not just a bracket.
No. That's the distance.
Okay.
Yeah. Well, square is bracket. Right?
Yeah.
That makes sense.
Yeah.
Okay, that's the inner product, right?
Yeah.
Okay. So here, whatever it will move, we know they always x squared plus y squared minus L squared equal to 0. Do you agree? You see, the x. So this is a distance that x squared y squared. So whatever you move, the x and y always change, but x squared plus y squared always equal to L squared. So that is this. That is the condition or equation or constraint for this case. So you need to familiar try to how to find that. I give you examples, and then I will give more since this is something new, maybe not really familiar. So now I'm going to give you more examples. The third one is a box slide down a slope. The box slides down a slope. Okay, so we have a slope here. This box, right? Now, if we set up x coordinates and the y is here, so you know that it will not leave this slope, right? So y always unchanged. And also z, right? So now means z we always equal to 0. Sorry, y always equal to 0. Do you agree? Only x change. Because only along, if I set x along on this slope, right? So you cannot, this box cannot leave the surface, and it is just a linear motion. It will not like this turn. If initially it's just gravitational, there's no any other force, just like this. So this is also the equation to give us the condition for the constraint. Number 4, let's consider a particle is constrained on the inner surface. Inner surface of a sphere. Okay, so here we have a sphere. You can set up the whatever x, y, z. X, y, z. And then the particle is here, inner, because inner surface, right? You cannot out of the surface, so always move on the surface, whatever it move. So in this case, we have x, each time we have x, y, z coordinates. And this x, y, z coordinates always equal to r, the square, right? So that means it cannot leave off the surface. That means whatever the particle in any position on the surface, the x squared plus y squared is always equal to r squared. Or I just write minus r squared equal to 0. Do you agree? That's another constraint. So this is easier. We do not know how to determine the constraint force, but we know the effect to restrict motion we can write by analyze the type of constraint, right? Okay, these 4 are example, and you can see those are only depend on given the relation constraints only function of the coordinates. So that is this case. That is polynomial. Yes.
In the third example, there is you've written z equals to 0.
Yes.
So why is that? Again, I'm sorry.
That is z. Okay.
Yeah.
Z is out of plane, right?
It's not coming
In
towards
3D.
Okay.
In 3D.
Oh, it's 3D.
Yeah.
Yeah.
It's 2D.
It's not 2D.
It's 3D. Okay. Yes, that's 3D. So the z is out of plane, perpendicular to this blackboard.
Okay.
Let me do this way. So here.
If you're considering to
Yeah, if you see that is like this motion, that is there's a z. But this is just this motion, right? So that is only along this way, and it cannot get out. So the y is 0, and it cannot go this direction, just along this direction. So I'm going to set up the direction motion of as x-axis, and it will not go to this turn. That makes sense? If yes, then z is not equal to 0. Yeah, this is really. So I just consider simple case, right?
This
All right.
basically a 2D problem.
I think, let me see, number 5. One more. I know that give more examples of those case. Number 5 example is the 2 blocks connect to 3 pulleys through a rope. Okay, now I'm going to ask you, so see whether you can give me the equation of the constraint. Okay, let me give you this radius r. This is also r. This is a lower r. And So we have two loops, right? Rows, right? Loops, right? This is L1. This is from here. Oh, this, yeah. It's from here to here to here, and this is L2. Okay. And then I'm going to write, since I'm going to set up this, let me see, I'm going to set up this 0 is here, so this distance is x4, and from here to here is x3, x1, so this particle one, x1, and from here to center of this is x, no, this is x3, sorry. This is given m3, m4, x4, and this one, x2. All right. You can write down. So let me first, simple case, x2 equal to, that is constant, right, always equal to L2, this one. Now, another loop is from here to here and to here. So, those add together is equal to the L1, right? Now, let's look. So here, this one is x1. And then, okay, so here we have a pi r, right, to here. And from here to here, it is x4 minus x3, right?
Yes.
So then here we have a pi r, and then we have another pi r, so twice, right? I think I forgot. This is this one, but we have x4. This part, right? This one is x4 minus x3. So you have I think I have an x3. I need also this part, so I forgot. Right? That equal to L1, so minus L1 equal to 0. Or here is, so I have two equations. All right, this is another example. How can you find the equation of a constraint? Okay, that is the one case we call this holonomic, and the opposite, the non-holonomic constraint is others. All the other constraint except this holonomic, right? So that means if we cannot find this relation to that constraints, we all belong to this. Examples is like this, not only the position, but also maybe velocity or only velocity. Or sum of position, but it is not equal, not equal to 0, something, right? Now let's do examples. Some examples you can see what we call the non-holonomic. Example 1. Okay, let's consider ruling without sliding. That is also very familiar. We know this type of motion, right? Without sliding. So we have a slope, we incline, we have either the ball or a disc. Okay, with this, right? Down to with the center of mass. If we say this omega equal to theta dot, which suppose this is a radius A, and this is a theta, right? So if we say that the ruling without sleeping means that the center of mass velocity equal to the rotation velocity, right? And this potential is relative 0. So we have this. And now you can see this constraint if you say. So that are the function of velocity, now coordinates. So these are not the holonomic, must be non-holonomic constraint. Another example like a gas in the container. So let's look at the gas. Gas in a container. Suppose it's a cubic, so we have L, right? So the particles inside move randomly, any position, any direction. Then what is constraint for the particle? Okay, xi, each particle we have is s particle, gs particle. Its xi cannot get out of this box, right? So larger or equal to 0, smaller or equal to L, or Lx if it's, let's select, if not cubic, Lz, Lx. I from 1 to n particle. So we have how many? We have a lot of. But this is not equal. This is just a limit within some range, so that is not holonomic. Similarly, the y I is also limited, and zi is limited. And those equation constraint is non-holonomic. Another case, which we are also familiar, if we have a S sliding down off a ball, ice sliding off. So we have a ball, and here suppose we have an S here, and this will be located here. And then this ball is spherical, so suppose this radius is A. Then any position here, this one is any, if at here is R, right? If off, so that is R. So we have R always, okay, R squared, this is R squared minus A squared always either equal. If it's on the surface, R squared equal to A squared, or R equal to A, the magnitude R. But if out of this ball, the R is from this center, right? It's always larger than A. So those equation or constraint, or this constraint we call this non-holonomic constraint. Another way to classify the constraint is in terms of time. If it is dependent on time or independent time, we can say that is scleronomic or reonomic. So even for the holonomic, this case is dependent on time. This is independent time. So we have we can say in terms of dependent on time or not. So here we have number 3 is scleronomic constraint, which is independent of time. Okay. And then oppositely, it depends on time like this. We call this okay. I think that example, give you example. I think the rigid examples, right? Example. Rij is Ri minus Rj squared, right? Second one, so this does not depend on time. Second one, we have a double pendulum. Okay, here we have a shading, and we have a first this pendulum here, and then this is a M1, M2, L1, L2, theta 1, theta 2. Okay, here you can see if this is a x1, y1, this is a x2, y2. So we have x1 squared plus y1 squared minus L1 squared equal to 0, right? That is whatever change, the distance always keeps same. Second one, so this does not depend on time, and this one is x2 minus x1 square plus y2 minus y1 square minus L2 square equal to 0, right? So this distance is x2 minus x1, and the vertical is y2 minus y1. And those are independent of time. Therefore, we say that are the scleronomic constraint. So now this one, for this case, we call the number 4 is which depend on time. Geonomic. That is depend on time. Okay, example. Let's see. Two examples. One is now we still consider simple pendulum, but now the joint also move, not the fix. Simple pendulum with the pivot point motion and go. And then goes simple harmonic. Motion. Okay, looks like this. Still simple pendulum, but now we have, say this is the pivot point, and we have the simple pendulum here, M with X, Y, and we have a L here, we have a theta. Now, this part also move, oscillate, right? So that is like oscillate like XT, YT, which is like X naught cosine omega T. So in this case, we have the constraint. We still keep this X minus XT anytime, right? Square plus Y minus YT square equal to, again, minus L equal to 0. That is key. But we have another one, this one. So XT equal to X naught cosine omega T. So now, this one give a time. That means if you substitute into here, replace, you will find this equation has a time dependent, right? So that is the number 4 case, or we classify in terms of laser dependent on time in part. Second one, is again a pendulum. I think that's enough. I will simply, so that's exactly another. So a bead sliding uniform formally rotate right. Okay, so that means we have a wire here. Now the bead is inside. Suppose this is just remove all this. Okay, any question?
In the previous example,
Yeah.
if you say, looking at the arrow, it seems as if xt is varying, but yt is constant, right?
Oh, okay, yes. So yeah, you're right. But I just write down in general, so yes, this is 0. Yes, only xt. If we just horizontal, yes. So that is, you're right. I think, right, yes. So this one does not need it, but in general, suppose that you're right. So now let's come to this. So this one bead is moved along the wire. The wire has a rotation. Omega t. In this case, we found that any case, so that any case x and y is always the r. Suppose this is r. That's r as function time, because the r will rotate, right? So the r as function time, x for given r is rt and cosine omega t, and y is rt sine omega t. So that constraint give us this time dependent. Okay, I think I can only stop here, and then we go through. Once we classify this type of the constraint, then we go back to see the equation of motion, how we deal with those, and how to overcome the difficulty come from the constraint force. And then you will see we are going to introduce the Lagrangian and Lagrange equation. All right.